Hello everyone, welcome to today's session. In the last session, we covered the KNN algorithm. So today's topic is Naive Bayes. So first, let me tell you in a word full of machine learning and artificial intelligence surrounding almost everything around us. Classification and prediction is one of the most important aspects of machine learning. So before moving forward, let's have a quick look at the agenda. I'll start off this video by explaining to you guys what exactly is naive biased. Then we'll end what is Bayes theorem, which serves as a logic behind the naive biased algorithm. Moving forward, I'll explain the steps involved in the naive biased algorithm one by one, and finally at the finish of this video with a demo on the naive Bayes using a SQL own package. Now, Naive Bayes is a simple but surprisingly powerful algorithm from penetrative analysis. It is a classification technique based on Bayes theorem with an assumption of independence among predictors. It comprises of two parts, which is naive and biased. In simple terms, Naive Bayes classifier assumes that a presence of a particular feature in a class is unrelated to the presence of any other feature, even if these features depend on each other or upon the existence of the other features. All of these properties independently contribute to the probability whether a fruit is an apple or an orange or a banana. So that is why it is known as naive. Now the naive Bayes model is easy to build and particularly useful for every large data sets. In probability theory and statistic Bayes theorem, which is already known as the Bayes law or the Bayes rule, describes the probability of an event based on prior knowledge of the condition that might be related to the event. Now, Bayes theorem is a way to figure out conditional probability. The conditional probability is the probability of an event happening given that it has some relationship to one or more other events. For example, your probability of getting a parking space is connected to the time of the day you park, where you park, and what conventions are you going on at that time. Bayes theorem is slightly more nuanced in a nutshell. It gives you an actual probability of an event given information about the test. Now, if you look at the definition of Bayes theorem, we can see that given a hypothesis H and the evidence E, Bayes term states that the relationship between the probability of the hypothesis before getting the evidence, which is the P of H, and the probability of the hypothesis after getting the evidence, that P of H given E is defined as probability of E given H into probability of H divided by probability of E. It's rather confusing. So let's take an example to understand this theorem. So suppose I have a deck of cards, and if a single card is drawn from the deck of playing cards, the probability of the card is a king is 4 by 52, since there are 4 kings in a standard deck of 52 cards. Now if king is an event, this card is a king. The probability of king is given as 4 by 52, that is equal to 1 by 13. Now if the evidence is provided, for instance someone looks at the card, that the single card is a face card, the probability of king given that it's a face can be calculated using the Bayes theorem by this formula. Since every king is also a face card, the probability of face given that it's a king is equal to 1. And since there are 3 face cards in each suite, that is a chat, king and queen, the probability of the face card is equal to 12 by 52, that is 3 by 13. Now using Bayes theorem, we can find out the probability of king given that it's a face, so our final answer comes to 1 by 3, which is also true. So if you have a deck of cards which has only faces, now there are three types of faces, which are the chat, king and queen. So the probability that it's the king is 1 by 3. Now this is simple example of how Bayes theorem works. Now if we look at the proof as in how this Bayes theorem evolved. So here we have probability of A given P and probability of B given A. Now for a joint probability distribution over the sets A and B, the probability of A intersection B, the conditional probability of A given B is defined as the probability of A intersection B divided by probability of B. And similarly, probability of B given A is defined as probability of B intersection A divided by probability of A. Now we equate probability of A intersection B and the probability of B intersection A as both are the same thing. Now from this method, as you can see, we get our final Bayes theorem proof, which is the probability of A given B equal probability of B given A into probability of B divided by the probability of A. Now while this is equation that applies to any probability distribution over the events A and B, it has a particular nice interpretation in case where A is represented as a hypothesis H and B is represented as some observed evidence E. In that case, the formula is P of H given is equal to P of E given H into probability of H divided by probability of E. Now this relates the probability of hypothesis before getting the evidence, which is P of H, to the probability of the hypothesis after getting the evidence, which is P of H given E. For this reason, P of H is known as the prior probability, while P of H given E is known as the posterior probability, and the factor that relates the two is known as the likelihood ratio. Now using this term, Bayes theorem can be rephrased as a posterior probability equal the prior probability times the likelihood ratio. So now that is the maths which is involved behind the Bayes theorem. Let's see how we can implement this in a real life scenario. So suppose we have a data set in which we have the outlook, the humidity, and we need to find out whether we should play or not on that day. So the outlook can be sunny, overcast, rain, and the humidity high, normal, and the wind are categorized into two phases actually, which are the weak and the strong winds. The first of all, we create a frequency table using each attribute of the dataset. So the frequency table for the outlook looks like this. We have sunny, overcast, and rainy. The frequency table of humidity looks like this, and the frequency table of wind look like this. We have strong and weak winds and high and normal ranges for humidity. So for each frequency table, we will generate a likelihood table now. Now the likelihood table contains the probability of a particular day. Suppose we take the sunny and we take the play as yes and no. So the probability of sunny given that we play yes is 3 by 10, which is 0.3. The probability of x, which is the probability of sunny, is equal to 5 by 14. Now these are all the terms which are just generated from the data which we have here, and finally the probability of yes being 10 out of 14 So if we have a look at the likelihood of yes, given that it's sunny, we can see using Bayes theorem. It's the probability of sunny given yes into probability of yes divided by the probability of sunny. So we have all the values here calculated. So if you put that in our Bayes theorem equation, we get the likelihood of yes as 0.59. Similarly, the likelihood of no can also be calculated here is 0.40. Now similarly, we are going to create the likelihood table for both the humidity and the wind. There's a humidity, the likelihood for yes given the humidity is high is equal to 0.42 and the probability of playing no given the event is high is 0.58. Similarly, for table wind, the probability of yes given that the wind is weak is 0.75 and the probability of no given that the wind is weak is 0.25. Now suppose we have a day which has high rain, which has high humidity and the wind is weak. So should we play or not? That's our reason for that. We use the Bayes theorem here again. The likelihood of yes on that day is equal to the probability of outlook rain given that it's a yes into probability of humidity given that say yes, and the probability of wind, that is we are given that we are playing yes into the probability of yes, which equals to 0.019, and similarly the likelihood of no on that day is equal to 0.016. Now if we look at the probability of yes for that day of playing, we just need to divide it with the likelihood sum of both the yes and no. So the probability of playing tomorrow, which is yes, is 5, whereas the probability of not playing is equal to 0.45. Now this is based upon the data which is already have with us. So now that you have an idea of what exactly is naive based, how it works, and we have seen how it can be implemented on a particular data set. Let's see where it is used in the industry. Let's start it with our first industrial use case, which is news categorization, or we can use the term text classification to broaden the spectrum of this algorithm. News on the web is rapidly growing in the era of information age, where each news site has its own different layout and categorization for grouping news. Now this heterogeneity and classifies the news articles according to the user preference is a formidable task. Companies use web crawlers to extract useful text from HTML pages, the news articles, and each of these news articles is tokenized. Now these tokens are nothing but the categories of the news. Now in order to achieve better classification results, we remove the less significant words which are the stop words from the documents or the articles, and then we apply the Naive Bayes classifier for classifying the news contents based on the news. Now, this is by far one of the best examples of Naive Bayes classifier, which is spam filtering. Now, the Naive Bayes classifier is a popular statistical technique for email filtering. They typically use a bag of words featured to identify at the spam email, an approach commonly used in text classification as well. Now, it works by correlating the use of tokens but the spam and not spam emails, and then the Bayes theorem, which I explained earlier, is used to calculate the probability that an email is or not a spam. So Naive Bayes spam filtering is a baseline technique for dealing with spam that container itself to the emails needs of an individual user and give low false positive spam detection rates that are generally acceptable to users. It is one of the oldest way of doing spam filtering with its root in the 1990s. Particular words have particular probabilities of occurring in spam email and legitimate email as well. For instance, most email users will frequently encounter the word lottery or the lucky draw of a spam email, but will them see it in other emails. The filter doesn't know this probability in advance and must be trained so it can build them up. To train the filter, the user must manually indicate whether a new email is spam or not. For all the words in each screening email, the filter will adjust the probability that each word will appear in a spam or legitimate email in a database. Now, after training, the word probabilities, also known as the likelihood function, are used to compute the probability that an email with a particular set of words belongs to either category. Each word in an email contributes to the email spam probability. The contribution is called the posterior probability and is computed again using the Bayes theorem. Then the email spam probability is computed over all the verses in the email, and if the total exceeds a certain threshold, say 90 or 95%, the filter will mark the email as spam. Now, object detection is the process of finding instances of real world objects such as faces, bicycles, and buildings in images or video. Now, object detection algorithms typically use extracted features and learning algorithms to recognize instances of an object category. Here again, Naive Bayes plays an important role in categorization and classification of objects. Now, the medical area produces an increasingly voluminous amount of electronic data, which is becoming more and more complicated. The produced medical data has certain characteristics that make the analysis very challenging and attractive as well. Among all the different approaches, the naive Bayes is used. It is the most effective and efficient classification algorithm and has been successfully applied to many medical problems. Empirical comparison of Naive Bayes versus 5 popular classifier on 15 medical datasets shows that Naive Bayes is well suited for medical application and has high performance in most of the examined medical problems. Now, in the past, various statistical methods have been used for modeling in the area of disease diagnosis. These methods require prior assumption and are less capable of dealing with massive and complicated nonlinear and dependent data. One of the main advantages of the Naive Bayes approach, which is appealing to physicians, in that all the available information is used to explain the decision. This explanation seems to be natural for medical diagnosis and prognosis. That is, it is very close to the way physician diagnoses patients. Now, the weather is one of the most influential factors in our daily life, to the extent that it may affect the economy of a country that depends on occupation like agriculture. Therefore, as an countermeasure to reduce the damage caused by uncertainty in weather behavior, there should be an effective way to predict the weather. Now, weather forecasting has challenging problem in the meteorological department for years. Even after technological and scientific advancement, the accuracy and protection of weather has never been sufficient. Even in current day, this domain remains as a research topic in which scientists and mathematicians are working to produce a model or an algorithm that will accurately predict the weather. Now, a Bayesian in approach-based model is created by where posterior probabilities are used to calculate the likelihood of each class label for input data instance, and the one with the maximum likelihood is considered as a resulting output. Now, earlier we saw a small implementation of this algorithm as well, where we predicted whether we should play or not based on the data which we had collected earlier. Now, there is a Python library which is known as scikit-learn. It helps to build Naive Bayes and model in Python. Now, there are three types of naive Bayes model under scikit-learn library. The first one is the Gaussian. It is used in classification and it assumes that the feature follows a normal distribution. The next we have is multinomial. It is used for discrete counts. For example, let's say we have a text classification problem and here we considered Bernoulli trials, which is one step further, and instead of words occurring in the document, we have counted how often a word occurs in a document. You can think of it as a number of times the outcome number is observed in the given number of trials. And finally, we have the Bernoulli types of naive Bayes. The binomial model is useful if your feature vectors are a binary bag of words model where the ones and the zeros are words that occur in a document and the words which do not occur in a document respectively. Based on their dataset, you can choose any of the given discussed model here, which is the Gaussian, the multinomial, or the Bernoulli. So let's understand how this algorithm works and what are the different steps one can take to create a Bayesian model and use Naive Bayes to predict the output. So here, to understand better, we are going to predict the onset of diabetes. Now this problem comprises 768 observation of medical details of Pima Indian patients. The record describes instantaneous measurement taken from the patient such as the age, the number of times pregnant, and the blood work group. Now all the patients are women aged 21 and older, and all the attributes are numeric, and the units vary from attribute to attribute. Each record has a class value that indicates whether the patient suffered on onset the diabetes with 5 years or the measurements. Now these are classified as 0. Now I have broken the whole process down into the following steps. The first step is handling the data, in which we load the data from the CSV file and split it into training and test datasets. The second step is summarizing the data, in which we summarize the properties in the training dataset so that we can calculate the probabilities and make predictions. Now the third step is making a particular prediction. We use the summaries of the dataset to generate a single prediction, and after that we generate predictions given a test dataset and summarized training dataset. And finally, we evaluate the accuracy of the predictions made for a test dataset as a percentage correct out of all the predictions made, and finally we tie together and form our own model of Naive Bayes classifier. Now the first thing we need to do is load our data the data is in CSV format without a header line or any quotes. We can open the file with the open function and read the data lines using the read function in the CSV module. Now we also need to convert the attributes that we are loaded as string into numbers so that we can work with them. So let me show you how this can be implemented. Now for that you need to install Python on a system and use the Jupyter notebook or the Python shell. I am using the Anaconda Navigator, which has all the things required to do the programming in Python. We have the Jupyter Lab, we have a notebook, we have the Qt console, even we have a RStudio as well. So what you need to do is just install the Anaconda Navigator. It comes with the pre-installed Python also. So the moment you click launch on the Jupyter notebook, it will take you to the Jupyter homepage in a local system, and here you can do programming in Python. So first we need to load the dataset. So I am creating a function to load CSV. Now before that we need to import a certain CSV, the math and the random method. So as you can see, I have created a load CSV function which will take the Pima Indian Diabetes data.csv file using the csv.read method, and then we are converting every element of the dataset into float. Originally all the ends are in string, but we need to convert them into floats for all calculation purpose. Next, we need to split the data into training dataset that Naive Bayes can use to make the predictions, and this dataset that we can use to evaluate the accuracy of the model. We need to split the dataset randomly into training and testing dataset in the ratio of usually 70 to 30. But for this example, I am going to use 67 and 33. Now 70 and 30 is a ratio for testing algorithms, so you can play around with this number. So this is our split dataset function. Now the Naive Bayes model is a summary of the data in the training dataset. Now this summary is then used while making predictions. Now the summary of the training data collected involves the mean, the standard deviation for each attribute by class value. Now for example, if there are 2 class values and 7 numerical attributes, then we need a mean and the standard deviation for each of these 7 attributes and the class value, which makes the 14 attributes summaries. So we can break the preparation of this summary down into the following subtasks, which are separating data by class, calculating mean, calculating standard deviation, summarizing the data sets, and summarizing attributes by class. So the first task is to separate the training dataset instances by class value so that we can calculate statistics for each class. We can do that by creating a map of each class value to a list of instances that belong to the class and sort the entire dataset of instances into the appropriate list. Now the separate by class function is just the same. So as you can see, the function assumes that the last attribute is the class value. The function returns a map of class value to the list of instances. Next, we need to calculate the mean of each attribute for a class value. Now the mean is to central middle or a central tendency of the data, and we use it as middle of our Gaussian distribution when calculating the probabilities. So this is our function for mean. Now we also need to calculate the standard deviation of each attribute for a class value. The standard deviation is calculated as a square root of the variance, and the variance is calculated as the average of the square differences for each attribute value from the mean. Now, one thing to note here is that we are using N1 method, which subtracts 1 from the number of attributes value when calculating the variance. Now that we have the tools to summarize the data for a given list of instances, we can calculate the mean and standard deviation for each attribute. Now that function group the value for each attribute across our data instances into their own list so that we can compute the mean and standard deviation value for each attribute. Now next comes the summarizing attributes by class. We can pull it all together by first separating our training datasets into instances grouped by class, then calculating the summarize for each attribute. Now we are ready to make predictions using the summarize prepared from our training data, making patients involved in calculating the probability that a given data instance belong to each class, then selecting the class with the largest probability as a prediction. Now we can divide this whole method into 4 tasks, which are calculating Gaussian probability, density function, calculating class probability, making a prediction, and then estimating the accuracy. Now to calculate the Gaussian probability density function, we use the Gaussian function to estimate the probability of a given attribute value given a node mean and a standard deviation of an attribute estimated from the training dataset. As you can see, the parameters x, mean, then the standard deviation. Now in the calculate probability function, we calculate the exponent first, then calculate the mean division. This lets us fit the equation nicely into 2 lines. Now the next task is calculating the class properties. Now that we can calculate the probability of an attribute belonging to a class, we can combine the probabilities of all the attribute values for a data instance and come up with a probability of the entire data instance belonging to the class. So now we have calculated the class properties. It's time to finally make our first prediction. Now we can calculate the probability of the data instance belong to each class value, and then we can look for the largest probability and return the associated class, and for that we are going to use this function predict, which uses the summaries and the input vector, which is basically all the probabilities which are being input for a particular label. Now finally, we can estimate the accuracy of the model by making predictions for each data instance in our test data. For that, we use the get predictions method. Now this method is used to calculate the predictions based upon test datasets and the summary of the training dataset. Now the prediction can be compared to the class values in the test dataset, and classification accuracy can be calculated as an accuracy ratio between the zeros and the 100%. Now the get accuracy method will calculate this accuracy ratio. Now finally, to sum it all up, we define our main function. We can call all this method which we have defined earlier one by one to get the courtesy of the model which we have created. So as you can see, this is our main function in which we have the file name. We have defined the split ratio, we have the dataset, we have the training and test dataset. We are using the split dataset method. Next, we are using the summarized by class function using the get protection and the get accuracy method as well. So guys, As you can see, the output of this one gives us that we are splitting the 768 rows into 514, which is the training, and 254, which is the test dataset rows. And the accuracy of this model is 74%. Now we can play with the amount of training and test datasets which are to be used. So we can change the split ratio to 70s, to 30 and 80s and to 20 to get different sorts of accuracy. So suppose I change the split ratio from 0.67 to 0.8. So as you can see, we get an accuracy of 77%. So splitting it into 0.8 gave us a better result, which was 77%. So this is how you can implement Naive Bayes Gaussian classifier. These are the step-by-step method which you need to do in case of using the Naive Bayes classifier. But don't worry, we do not need to write all these many lines of code to make a model. This is the way to scikit-learn library comes into picture. The scikit-learn library has a predefined method, or as say a predefined function of Naive Bayes, which converts all these lines into merely just 2 or 3 lines of codes. So let me just open another Jupyter notebook. Now here we are going to use the most famous dataset, which is the Irish dataset. Now the Irish flower dataset is a multivariate dataset introduced by British statistician and biologist Roland Fisher, and based on the fish is a linear discriminant model. These dataset become a typical test case for many statistical classification technique in machine learning. So here we are going to use the Gaussian NB model, which is already available in sklearn. As I mentioned earlier, there were 3 types of Naive Bayes, which are the Gaussian, multinomial, and the Bernoulli. So here we are going to use the Gaussian NB model, which is already present in the sklearn library, which is the scikit-learn library. So first of all, what we need to do is import the sklearn dataset and the metrics, and we also need to import the Gaussian NB. Now once all these libraries are loaded, we need to load the dataset, which is the Irish dataset. The next thing we need to do is fit a Naive Bayes model to this dataset. So as you can see, we have so easily defined the model, which is the Gaussian NB, which contains all the programming which I just showed you earlier, all the methods which are taking the input, calculating the mean, the standard deviation, separating it by its class, and finally making predictions, calculating the prediction accuracy. All of this comes under the Gaussian NB method, which is already present in the sklearn library. We just need to fit it accordingly to the dataset which we have. So next, if we print the model, we see which is the Gaussian NB model. The next thing we need to do is make the predictions. So the expected output is dataset.target, and the predicted is using the predicted model, and the model we are using is the Gaussian NB here. Now to summarize the model which was created, we calculate the confusion matrix and the classification report. So guys, as you can see the classification to provide, we have the precision of 0.96, we have the recall of 0.96, we have the F1 score and the support, and finally if we print our confusion matrix, as you can see, it gives us this output. So as you can see, using the Gaussian NB method, just putting it in a model and using any of the dataset, fitting the model which you created into a particular dataset and getting the desired output is so easy with the scikit-learn library. So this is all about the theoretical and practical session of Naive Bayes algorithm. I hope your doubts have been cleared. Still, if you have any doubt, you can drop your doubts in the comment section. Thank you so much for watching.